It is with great pleasure that we are presenting our work on classifying dyads for militarized conflict analysis at the Conference on Empirical Methods in Natural Language Processing 2021. This is joint work between ETH Zurich, MIT, EPFL and the University of Cambridge. This presentation is structured into two parts. In the first part, we focus on data for militarized conflict analysis and turn to the classification of dyads in the second part. We start by discussing the limited availability of data in the field of quantitative peace and conflict studies. This serves as motivation for our data acquisition pipeline. The first part concludes with a presentation of our newly compiled graph and text-based dataset, which we refer to as Conflict Wiki. The limited availability of data for conducting analyses of militarized conflict represented a primary motivation for this research. While there exists a growing NLP community concerned with conflict event data, we found that a majority of research focuses on event extraction and event type coding. Less research focuses on the subsequent analysis and modeling of the extracted data. Among the few analytical works, most are concerned with predictive tasks, and less with operationalizing or validating established theories from peace and conflict studies. This may be attributed to the fact that most data is sourced from online newspapers which impose copyright limitations. As a consequence, only few event datasets offer full-text event descriptions beyond news article headlines. Most datasets are instead limited to tabular data featuring meta-information on extracted event types, dates, locations, and actors. Associating the individually extracted events with their overarching long-term conflict or only filtering out duplicate event entries requires complex coreference resolution. For these reasons, we make an effort to compile a semantically richer and freely available dataset comprising text and graph-based features. To this end, we consider the Wikipedia subcategory 21st Century Conflicts by Year, which offers a collection of all conflict articles from 2001 to 2021. First, we retrieve all articles in this subcategory and all of its subcategories recursively up to a depth of 4 levels. Having retrieved articles, we filter them based on a precise militarized conflict criterion. Wikipedia articles on militarized conflict, specifically their info boxes, are unified by a military conflict template as displayed on the left-hand side. Each info box features metadata such conflict name, place, date, but also involved warring parties indicated by the combatant tag. There may be 2 or more combatants which are displayed as belligerents in the info box. Each belligerent comprises 1 or more entities that are united as allies in the particular conflict. Entities assigned to different belligerents are enemies. Almost all entities are hyperlinked to their own Wikipedia articles, which allows us to retrieve not only conflict, but also entity articles. Using the link structure between the retrieved Wikipedia conflict and entity articles allows constructing a conflict graph. We start with the belligerent partitions of different conflicts. An entity may of course occur in multiple conflicts. From all combinations of belligerents in a conflict, we construct a list of entity pairs, so-called dyads. Finally, we aggregate dyads across conflicts into a graph where nodes are entities and edges are conflicts. We label an edge as allies if, across all conflicts they partook together, the 2 entities have been allies strictly more often than enemies, otherwise the edge is labeled as enemies. Note that entities that do not co-occur in a conflict have no edge between them. This figure shows a small subset of the resulting aggregated graph. Each node represents an entity. Each edge represents the relationship of 2 entities that participated together in at least one conflict. Green edges indicate an ally and red an enemy relationship. The edge line width is proportional to the number of conflicts shared by both entities. Besides this rich topological conflict structure, we harness the text-based content of the Wikipedia articles. Each node is represented by the article corresponding to that respective entity such as Mali or France. Yet, each edge is represented by the mean of all corresponding conflict articles. As article representations, we consider TF-IDF feature vectors. To this end, we filter all tokens that are neither nouns or adjectives and lemmatize all tokens. Further, we remove all context indicative tokens such as locations, dates, nationalities, political groups and organizations, but keep world religions. This leaves us with interpretable representations free of contextual clues as shown on the table on the right-hand side. The graph and text-based data constitute a rich dataset covering militarized conflicts, which we term Conflict Wiki. We will briefly demonstrate our interactive dashboard that allows exploring the data. The dashboard visualizes a randomly sampled subset. We can hover nodes and edges to display their names. Further, we can click nodes and edges to display their corresponding Wikipedia articles. When clicking a thick edge representing multiple conflicts, We can select among them. There also exists the functionality to sample a new subset of the data on demand. In the second part of this presentation, we demonstrate how our novel text and graph-based dataset allows for more theory-driven forms of militarized conflict analysis. In particular, we present the task of classifying dyads as allies or enemies. To this end, we first introduce the concept of dyadic and systemic correlates of conflict. Next, we propose a quantitative operationalization of these concepts. Finally, we discuss our results and other interesting findings. Understanding the origins of militarized conflict is a complex, yet important undertaking. Existing research seeks to build this understanding by considering dyadic causes between entity pairs and systemic causes among multiple entities. Dyadic pertains to bilateral origins such as entity-specific idiosyncrasies, competing ideologies between two entities. For instance, dyadic origins have been attributed to the Mali War. The war may have been spawned from differing cultural and ideological identities between the Azawad liberation movement and the Malian government. Systemic, on the contrary, pertains to broader multilateral relationship networks. For instance, the intervention of France in the Mali War may partly be attributed to NATO's close diplomatic ties with the Economic Community of West African States. Dyadic and systemic origins are difficult to operationalize and intrinsically entangled. We make an attempt to construct features that encode the notions of dyadic and systemic. To this end, we consider the dyad graph, G, introduced in the first part of this presentation. The dyad graph consists of entity nodes, N, and labeled edge relationships, E. The graph can be equivalently represented by the set of all dyads, capital D. Each dyad, small d, is a quadruple consisting of two involved entities, small u and small v, the conflict representation, small e, and the label, small y. As systemic features, we consider the graph neighborhood in which two entities are embedded. Hence, we can think of systemic features as those that are exposed by the dyad graph, G, minus the dyad, Di, that is to be classified. Concretely, our systemic features are the representations of neighboring entities, the representations of their relationships, and the labels of those relationships. The larger scientific mission is to investigate whether, when analyzing a large corpus of conflicts, dyadic or systemic correlates of conflict are more prominent. We test this by training models to classify two entities as being enemies or allies. Operating on the dyad graph allows casting the problem as an edge classification task, to label edges. The models are given access to either only dyadic features or systemic features and are referred to as dyadic and systemic model respectively. Both models use Siamese-style neural network encoders. The systemic model uses a graph neural network to incorporate the network structure additionally. The ceiling model combines both models and is given access to all available features. This table presents the results of the dyad classification task. We report the mean F1 score and its standard deviation over 10 runs. The top half of the table compares the dyadic, systemic and ceiling model as well as a majority vote baseline. We find that the systemic model outperforms the dyadic model, and the ceiling model yields the best results. Additionally, we conduct an ablation study on the individual dyadic and systemic features. Specifically, we ask the question, out of all dyadic and systemic features, which ones are stronger correlates of militarized conflict? Our results suggest that the dyadic and systemic features we extracted from Wikipedia correlate with whether a pair of entities are allies or enemies. Indeed, we find that articles of allies are semantically more similar than enemies. This plot shows the top two principal components of TF-IDF representations of the four entity articles involved in the Mali War. Each belligerent is shown with the same symbol. We observe that the allies Mali and France are semantically more similar to each other than to their enemies. To gain further insights into the semantic similarity of allies and enemies, we select the 1000 pairs of section titles that most frequently co-occur among allies and enemies, for instance summary, and compute the cosine distance of their representations. The plot shows the average cosine distance between ally section pairs in green, and enemy ones in red. We find that the distance is, on average, lower between allies than between enemies at a significance level of 5% under a t-test. Within our dataset, textual similarity between two entities, thus, correlates negatively with the entity's propensity to conflict. Future work could introduce conflict priors on entities to incorporate so-called monadic causes and experiment with time-version Wikipedia articles in different languages. It may be insightful to study edges breaking structural balance theory, predicting missing edges instead of classifying them, and connecting the dataset with external event-level data. Thank you very much for watching.